result from the data, which agree very well with the model, which is 1. Okay. All right. So then you can ask further questions. So I try to study each component of the signal strength, each component of the coupling. And how about the width? So do I have a way I can estimate? Because I know that the Higgs itself is a really narrow particle. It's the order of MeV. So could I measure this quantity or verify this quantity? Then we have 2 approaches to do that. This is the approach proposed by Cowher and Astorino. This is a very creative idea. So the way they do is that if you try to write down the production cross-section of the the Higgs production at the Higgs peak value, and then you also try to calculate, because the Sennett Higgs and the standard model continue PP to ZZ production, they have the same final state. If you consider the box diagram of the standard model process, then you could actually have a interference between the continued Coulomb ZZ production and the Higgs Coulomb to ZZ diagram. So you could study by very different widths of the Higgs. Will that change the continued ZZ shape? And this is just to show one extreme example. If the red one is you put in the standard model Higgs, and if you try to inflate the standard model Higgs width by a factor of 25, you can see the shape of the continued Z resonance have a huge modification. Okay, this kind of interference effect. So what we can do is try to fit this shape to the data. Then we can extract what's the width of this new discovered particle. And this is the constraint we have. At the 95% confidence level, the expected limit of the Higgs width is 8.5, larger than the standard model Higgs width. But we observe at 4.2. So our observation is a downward fluctuation compared to the expectation value, which put quite a stringent constraint on the real Higgs mass itself is. So if you compare to just the MeV level, so now through this method, we have a constraint. The Higgs width is less than 17.4 MeV at 95% confidence level. Then the other way, we can put in an assumption that is we have a way to measure those visible decay channel. But how about the case that the Higgs decay to some invisible object that we cannot detect? Okay, that could be a semi-located, for example. So this is associated Z Higgs production. This is going to decay to dark matter kinetics. And this is a VBF production channel that Higgs decay to individual particle. So the signature will be you have a large missing key. So you can compare, you can see that if you try to introduce a large decay width of the Higgs decay to the individual particle, you can modify the missing key spectrum. So then we can use this method to constrain what's the component or understanding of the individual for Higgs decay will be. Just give you some idea. If you look at a case when Higgs decay to ZZ star and further decay to neutrino pair, and this is also Higgs decay to invisible final state. This is very small. It's only 0.12% restoration. So if you fit this and have a large coupling with Higgs, and you have a chance to see it, and could be quite convincing signature, different from the standard model. And this is the result. So both Atlas and CMS have carry out the result of the invisible Higgs measurement. And this is our understanding. The Atlas combined limit is about the French ratio of invisible Higgs decay is less than 37%, and CMS is less than 58%. One interesting is that we have this total width measurement from interference method. If you convert it to the decay width limit of the Higgs, it's actually comparable to this invisible Higgs search. Yeah. So if you combine the two methods, you can further basically improve the understanding of the invisible Higgs of the invisible width of the Higgs. So you can also do another reinterpretation. What happens is that now, because we put this assumption, Higgs decay to some dark matter candidate. So basically, this result can convert to the interaction, the strength of this vertex. Then we can compare to the typical dark matter research method. The idea is that you have dark matter interact with the nucleus. So we can calculate the dark matter nucleus scattering cross section. And you can put the constraint you derive from our measurement here, and to see how the limit of the nuclear Higgs, nuclear dark matter interaction will be in this plot. So here you see the three curves. These three curves are different assumptions of the nature of the wind dark matter is. So you can see that it is cut off at 125 GeV just because they cannot be heavier than the Higgs particle. So compared to the current dark matter search method, through this invisible Higgs measurement, you can actually put quite a stringent constraint on the dark matter nuclear interaction cross section, in particular for the very low mass of the dark matter. So this is a range that very difficult for the red dark matter search method could probe. Right? So this is what I want to talk about the standard model. Then I'll move on to the topic of beyond the standard model. So how much time is left? 35 minutes. Okay.
Can I have a question?
Yes.
You just show the invisible decay
Of Higgs,
to
yes.
neutrino is 0.12%.
Here.
And the current
The limit.
upper limit is almost 50%.
50%, right?
So how long do we have to wait to see this 0.1%?
Oh, you mean 0.12%?
Yeah.
Actually, I can show you later. I have
Okay.
some prediction. Okay. Right. So because I only have 35 minutes, so maybe I should jump to the question you want to ask. Yeah. So let me try to go to the what we can see beyond the current LHC. Okay. So give me a couple more minutes, then I can answer the question. Okay. So this is the current LHC program. So we already planned out all the way to 2040. Yeah. So at the time there will be a couple more generations of the PhD students, and I probably should retire around that time. Yeah. If I still survive. So here we are. So we are going to ready to start with round 2, and we will start with 13 TeV, and hopefully we can extend to 14 TeV if everything goes well. So we expect to accumulate 100% by 2018. Then we have another upgrade, which can really ramp up to 14 dB with the better higher velocity. So by 2022, we expect to access 300 Mbps on data. Then we have another long shutdown. By 2025, we will start the large Higgs collider to its expected low velocity. And we expect to just continue to run it forever, or maybe we have IRC at that time, or we discover some new physics. Then we decide that we should try to change our search strategy. But here we just put a number, so 3,000 Mbps. So what I'm going to show you later is that use these two numbers target the velocity, and let's try to estimate what's the sensitivity of some new physics. So I'll focus on the Higgs because that's the new particle we found, and it's quite interesting that if there's something new, it's very likely to start from the Higgs. So we want to press further how the Higgs coupling with the different sectors, including the self-coupling of the Higgs. For example, you could have some model predict this vertex, okay? But the production rate for either one of them, the two Higgs production, or through the fermion loop, or through the self-interaction, is very, very small. We need quite a lot of data in order to study this channel. So assume that we accumulate the 3,000 Mbps amount of data. So probably we're talking about 20 years from now, right? So what happened 20 years from now, what you can see? For example, if you consider the TD bar Higgs coupling, okay, we could expect we can collect TD bar Higgs coupling where Higgs, TD bar Higgs production channel and Higgs further decay to 2 photons. We could roughly have 100 of that. And we could have roughly 30 of TTH production where Higgs decay to 4 lepton. Okay? So this also gives you some idea if we are talking about if the measurement of the top coupling to the Higgs is a very important number you want to know. You really need a long time in order to get this number. Okay? It's not something you can get it 10 years from now. So that also means if you see some anomaly production of this channel show up, this is going to be extremely exciting. And just give you a reference number for Careway. At that time, we will have a roughly 3,400 Higgs to ZZ to 4 lepton to study the fine distribution of this production decay channel. So if we have a 3,000 Mbps, we can study the rate of decay. For example, Higgs decay to 2 muon, and we could establish 7 sigma significance. Yeah. So this also tells you that if we want to measure the muon coupling to Higgs directly, we don't need to wait for 3,000 Mbps. It could be earlier. And however, in terms of Higgs to Z gamma, so this have undergo the loop diagram over through the this polycoupling. So this is a really rare production. So even with 3,000 Mbps data, the expected observation significance is only 2 sigma. Okay. So then here it shows you the similar problem we showed earlier, the coupling strength. And the x-axis here shows the uncertainty, how you can constrain on each coupling strength. So in general, they are less than 10%. Okay, So including the theory uncertainty. Yeah. And if you just talk about the experimental uncertainty, it's less than 5%. Okay. So now we can try to evaluate how different kind of model, what's the possible modification on the coupling strength they could do. Yeah. So if you compare this number for some of the model, for example, 2x coupling model, okay, we have a chance like to constrain or to probe this kind of model by doing this coupling strength study. But it's generally very difficult to so for one of the channel, if you want to constrain those model through the Higgs coupling measurement and the Large Hadron Collider, it's quite a challenge. Okay. So invisible Higgs is here. If we have a 300 inverse Feynman, we can push the constraint to 20%. And then with another decade, we have a 3,000 inverse Feynman, we can push to 8%. So we probably need if we did not upgrade our machine, just run this machine this way. If you want to probe the Higgs to ZZ2 for new, it's a 0.12%. We probably need a century or more. So we need a more creative idea, like how to using the technology improvement to do a realistic analysis, right? But this is the case like 20 years from now, when we have a 3,000 Feynman, and we have some projection how the direct document search the document the nucleon scattering cross-section looks like compared to what could be constrained by the Large Hadron Collider. So we also have an interesting channel like variable changing neutral current, top decay, then top decay to the neutron plus Higgs. The 7 model have a prediction of 3 times 10 to the minus 15 differential ratio. This is extremely small. But you could easily introduce some beyond 7 model physics to enhance this differentiation. So this is one of the dream search channel we want to probe, have a chance to discover new field theory. So because we have a 3,400 ZZ24 lepton decay from the Higgs, this is a quite the largest physics sample. Then we can really play a very nice geometric study. And one of the things, for example, we can introduce new amplitude, which have CP up component. That some model only have a CP in component. So we can try to extract this CP up component and use this to infer the new physics. And with 3,000 inverse Feynman, we can reach to 0.037 of the CP violation coupling parameter. So we can also study what's the expectation of the additional Higgs. For example, in a two-subway model, you could have a pseudo-scalar Higgs, and it can decay to a Z boson plus Higgs boson, which further decay to 2 lepton plus 2d quark final state. So this channel is interesting in a way that it's sensitive to a low 10 beta case. And if you look at the differential ratio for different decay channel as a function of the pseudo-scalar Higgs, for the HZ channel, it has a particular region where it could be dominant, so between 250 to 350. So this is quite a nice channel to search for pseudo-scalar Higgs. Okay, but if it's beyond 350 GeV, and for this choice of 10 beta 2.5, it will be dominant by the TD bar channel. Okay, once it's beyond the top production ratio. this is a projection. If in some scenario, you can really constrain this model at the Swiss inverse minimum. Okay. So I will use the last 10 minutes to talk about the machine that beyond the typical logic Hedgehog kind of program I just explained to you. Now there are several efforts just ongoing actively talking about 100 TeV collider. So this is a worldwide effort, and if you ask the questions, once you have a 100 TeV collider, how that will change the picture of a new field search compared to 14 TeV collider. So this is a production cross-section of the QQ power tone as function of the power tone energy fraction versus beam energy. Okay, so let's just pick up one parameter to guide us. For example, let's pick this value, this 1 antibomb production cross-section value. Okay, so at this value, for the same integrated luminosity, for the 14 TeV collider, you can probe the energy of 3.2 TeV, but for the 100 TeV collider, you can probe 15 TeV energy. Okay, so this is the enhancement of the each beam energy into increase from 7 TeV to 50 TeV. Okay, so if we have this machine that would have energy go much higher, then we also have the power to probe the high energy particle. So the development of this 100 TeV collider is not just working alone, not just on the energy frontier. It is a coherent development closely with also the other the research area like cosmology frontier. So this will be the direction to go. In terms of dark matter, because now there are almost every few months there are new results with new gamma line observed in the sky. So this start changing the thinking about what the nature of dark matter. It's probably not just what we typically say the wind. Okay. The direction to go might be there's a hidden world with multiple states. That's why you have so many different gamma line. Okay, so more result you could try to see the Aspen just early this year. There are several discussions there. So this development, this thinking is coming from the observation on the universe. Okay, so the other important thing is that if you calculate the observed the rate, they are much higher than a typical wind could predict in terms of self-interacting dark matter. So that probably infer that the self-interacting dark matter has a new massive scale on this observation. So the interesting start going up for the electrosymmetry operating sector, that we might have a rich sector particles going on there. They could couple to a certain model particle via weakly interacting portals. Okay. Then this coming back to the Large Hadron Collider, or this the machine beyond the Large Hadron Collider. This is the machine that can produce a lot of particles compared to what we have today. In terms of Higgs, you can produce a factor of 10,000 more, and you can do the precision Higgs measurement. And this is a machine that can produce a lot of heavy top part, and you can do the rare decay study. And this is a machine that can give you extremely energetic QCD jet. You can study the the alpha is a running coupling constant to a very high energy. So this new 100 TeV machine, it gives us the access of the new particle to the 30 TeV laser scale. This is beyond what actually can do. The increased precision measurement with respect to large collider, I just showed some example, is much better. So it also gives us really access to a very rare process that we could probably search some phenomenon which is actually hidden inside large collider just because we don't have sufficient data. But all this development, 100 TeV collider will not be just solely just proposed without any foundation. So it will be coupled to this exciting time, not just the energy frontier, from the cosmology frontier and also from the intensity frontier. All of this coming up with a lot of interesting results. So the new physics might show up from those new experiments. For example, we will the Super Bell or the LHCb, they just now start giving a lot of well, LHC is starting a lot of new results. So Super Bell might be able to catch up to give us competitive results. Then we also have this new G-2 experiment coming up from Fermilab. So they could give us some access, give us energy scale, what the new physics will be. Or if we verify this various dark matter candidates, or this maybe even large collider give you some high mass observation. So all of this will just give us even stronger motivation, give us energy scale where you can try to build a large collider, even the next energetic electron collider. So 100 TeV is a conceptual energy. You use that, try to prepare yourself, project, and then where once you try to raise the energy, what kind of change you will have. Okay, so to me, I think this machine will, the critical problem will still be trying to understand the true nature of the electricity breaking. That is the nature of this argument that it will still stay there for a long time. Just this is, I want to share, I learned from the Magano that this is already a long-standing quest. Even the one of the father of the Sunday model already pointed out when he wrote the very early paper. So I would like to say that the Large Hadron Collider will be continue to be exciting, and it has to be work and couple closely with the other measurement, the other development in cosmology. Thank you.
I think that experimentalists can always talk about machines higher energy.
Yes.
I'm just curious, how did you come up with this number, 100?
As I said, it's an easy number to talk about.
It's an easy number to talk
Yes.
about. But you need a strong, very strong,
No.
convincing evidence. Otherwise, I don't think
Yes,
no
yes,
country
that-
will
that's
be
what-
valid. Okay.
I agree. My vision is that all these scientific collider, you talk about that, just you actually need to start to build about it right now. To prepare, once you have something really new discovered. I predict that this new machine will not be realized if we did not find any new physics. We need a guidance from other experiment. This other experiment, including the Large Hadron Collider, we need something new in order to really motivate to build this machine. But in terms of the technology, also preparation, we should start thinking about it right now. If we are going to build this machine, what's the